All right, let's then move on to the canonical ensemble, which is very exciting. So the microcanonical ensemble, we assumed that the energy of the system was constant, right? So E was constant. And then we figured out, using the principle of statistical mechanics, what the number of configurations were. And then from there, we figured out what the entropy was. And then from entropy, we derived everything else. It was very powerful. But it may not be the case where our system's energy is always constant. For example, consider the case where you have a reservoir, say a room, at some temperature T, and you have some hot cup of coffee or tea in the room, and then and the energy is being exchanged between the room and the cup of coffee all the time. And although there is some average energy of the coffee, which is always well defined, because there is like energy being transferred to and fro, there will be fluctuations. So what is important there is that energy is not constant, but we have some well-defined average energy, which is determined by the environment, the temperature of the environment, right? So this is very different from the assumption of the microcanonical ensemble. So we need to have more general applications of statistical mechanics. We need to consider this situation, and this is called the canonical ensemble. So let me set up the canonical ensemble more in a more well-defined way. So we assume that we have some reservoir, and the reservoir is a very large system, so large that it has many degrees of freedom, and it has a very well-defined temperature. So this is the reservoir, and we have a relatively small system. Let's call it S. And the system is connected to the reservoir by some impermeable but diathermal wall. Okay, so this is impermeable but diathermal wall. Impermeable means that particles cannot be exchanged between the system and the reservoir, but diathermal means that heat can be exchanged. Okay. Now, what we do is that we figure out, what is the probability of finding the system in a state E alpha. So what is the probability of finding the system S, in a state alpha, which has energy with energy E of alpha, okay? So what is the probability? That probability is given by some constant times the number of configurations that the reservoir can take. And if the total energy is E0, where the energy of the reservoir is E0 minus E alpha, okay? So this is a non-trivial statement I'm making here. And if you think about it carefully for a minute, this is quite a convincing argument.
So what does E naught stand for?
Right. E naught is the total energy of the reservoir and the system. And E alpha is very small. So E naught is much, much bigger than E alpha, okay?
E naught is not necessarily constant, right?
E naught
Since we're
is
doing,
constant, yes.
but
E naught is constant.
aren't we doing canonical ensemble? So like total
So
energy.
here we are applying the principle of statistical mechanics, right? Because our total energy is constant of the total system. You know, and some of the energy is being exchanged between the system and the reservoir, but the total energy is assumed to be constant. Okay.
Okay.
Yeah.
Yeah, I get it.
Right. Okay. So
Sir, I
so
didn't
this
get
is
the probability of alpha is equal to C omega r E naught minus E alpha.
right. So exactly. So what is this? This is the number of configuration that the reservoir can take, which is huge, at this energy. Of course, the probability that the reservoir will be in that at that energy is given by a number that is proportional to this, right? Number of configuration it can take. Because if I look at the volume in configuration space or whatever, then this will be the fraction of that volume.
So
And
I
this,
was wondering why didn't we consider the states of the system and instead consider the states of the reservoir to find out the probability.
uh, yeah, it's something that is going to become obvious in a second, because one of the assumptions that we are going to make is that the reservoir's temperature is constant, even though the system's energy can change, okay? Because the reservoir is large, if you dump some heat into it from the system, or if you take away some energy from it and dump it into the system, the temperature won't change. And that's something that we will use in a few moments, okay?
Oh, I see.
Because the temperature of the system will fluctuate, right?
Yes.
But the temperature of the reservoir, think of a cup of coffee, right? I mean, you know, the temperature of the room is not actually going to go up significantly when the coffee cools down, right? So that's something we will use. But very good question, yeah. All right, so let's expand the probability as a Taylor series in E alpha. So of course, instead of probability, we want to expand log of probability. Log is a very nice function, as we know. It's a monotonic function. So the log of PA is going to be given by some constant log of C. And then we have, say, the log of omega R evaluated in E naught. And then we have minus E alpha d of log of omega R d of E, and this thing is evaluated at E naught. And then we have minus E alpha squared divided by 2, and then D squared log of omega R d of E squared evaluated E naught, and so on and so forth. Okay. So now what we do is that we can apply our statistical, our microcanonical definition of entropy to the reservoir because it is so large. And then what we do is that we say, okay, we are going to use a definition of temperature, and then this is 1 over kBT. Okay, and now we use the fact that the assumption that the temperature of R remains constant. Okay? So if the temperature, so then we see that over here in the higher order term, in the second order and the third order term, there, this thing is going to give me 1 over temperature. So this is going to give me like derivative of temperature, and therefore with respect to E. And since the temperature is not going to change, for small fluctuations of energy, we can ignore all these higher order terms. Okay, so that's the trick that we use. And then we have just this term, and this term, right? And then what we do is that we can just take the antilog of exponential of this, and then we get P of E is e to the power minus E alpha by kBT divided by some normalization constant called Z. Okay, so all of this normalization comes from this term and this term, and this becomes 1 over kB of T. Okay?
Sir, that's Boltzmann's law, right?
Yes.
I mean,
we have just derived Boltzmann's.
Right.
So this is known as the Boltzmann distribution. Okay, the Boltzmann distribution, or the canonical ensemble.
They're used synonymously?
Apparently.
Oh.
So that divided by Z, is that the C and the...
Yes, the normalization constant, yes. We shall be discussing Z moment in a moment, yes. So, we haven't defined what C is, right? So we now have an opportunity to define what Z is, right? So what we are going to say is that, okay, we are going to assume that P of alpha, sum over all alpha, is 1. That defines what Z is. Then Z is going to be sum over alpha e to the power minus E of alpha by kBT, which we also write as sum over alpha e to the power minus beta E alpha. So beta is a commonly used term for 1 over kBT. It's the inverse temperature in units of 1 over kB. It has the dimension of energy, right? Beta has the dimension of energy. Sorry, inverse energy. Because otherwise, we need this to be dimensionless, right? And this normalization constant is known as the partition function. And we use the symbol Z for partition function because the name for the partition function in German starts with a Z. I forget what that name is, but it starts with a Z, okay?